GTC is a celebration of your work. GTC is about you. And as usual, this year again, you guys have given us an amazing conference. Now, during my time together with you this morning, I'd like to talk about 4 things. The first thing I want to talk about is NVIDIA's focus. I want to talk about the progress and the status of CUDA's development and deployment. And then I want to talk about 4, 5, 6 amazing announcements. And then lastly, a peek into the future. And of course, as always, with every NVIDIA conference, show you some great demos. So let's get started. NVIDIA is focused on 3 areas of computing where we believe we can make the greatest contribution to the future of computing and where we believe the greatest impact to computing will be. Those 3 areas are visual computing, parallel computing, and mobile computing. The Quadro brand is targeted at workstations and serves digital designers and creators. The Tesla brand goes into servers in the cloud and accelerates computing. I'm going to talk about some of these during my talk. Our personal computing brands are GeForce, which helps PC users enjoy their games, or anybody who just wants the best possible PC experience. And then our newest brand, called Tegra, is NVIDIA's SoC, or System on a Chip strategy. The CPU we use in Tegra is ARM. And the reason why we chose ARM is because it's simply the fastest growing CPU in the history of mankind, and it's the fastest growing CPU in the world today. It is the ISA of choice, the instruction set architecture of choice of mobile computing. And it's also the instruction set architecture of choice of the fastest growing operating systems in the world. It is very clear now, based on what we know and what we see in our roadmap, that mobile computing will be a completely disruptive force to all of computing. This is an area that I'm sure all of you have become much more aware, and this is an area where we believe great contributions to computing will happen. Now, mobile computing isn't just about a computer that you can take with you. Mobile computing is rather special. This is the first computer that is equipped with all kinds of sensors. Cameras, microphones, GPSs, accelerometers. This is the first computer that is context aware, situation aware. Who knows, maybe one of these days this computer will be self-aware. Because of all these sensors, mobile computing is going to be able to achieve and deliver the type of magical experiences that wasn't possible before. What we would like to do is to recognize that all of this data that's streaming in to the computer is processed in a way as such that we can deliver a magical and unexpected, a delightful experience to users. The combination of the processing that's done on the Tegra SoC, the Tegra processor on the mobile computer, as well as the Tesla processor in the cloud, will surely deliver a magical experience. We're really, really excited about that. So Quadro in the workstation, Tesla in the cloud, Tegra for mobile computing devices, and GeForce for PCs. Well, it's unlike us to do any kind of a conference without showing you the state-of-the-art of computer graphics. This year, the big deal, the big idea, is called tessellation. Tessellation takes simply a patch and displacement maps and complicated shaders and creates amazing geometric fidelity where there wasn't before. We've been working on all kinds of texture fidelity and all kinds of lighting effects over the years, but the geometry fidelity has stayed relatively constant. In order to make that happen, Fermi improved its geometric capability substantially, 6 times faster than our previous generation. In no GPU family before it have we made such a large leap in performance in one single area. Fermi is 6 times faster in geometric processing than the generation before it. We're about to show you now an application or a game that is not yet released. It's called HOX 2 from Ubisoft. HOX 2, well, HOX is a squadron that's sent into the Middle East to investigate the mysterious disappearance of nuclear weapons in the Middle East. Now, in this particular game, you can fly all kinds of great airplanes, from the F-22 Raptor to the A-10 Thunderbolt. Each level of the game is approximately 128 square kilometers, where each polygon comes all the way down to 2 meters. So within each level, if we render the entire level at one time, would represent 4 billion triangles. All of that is so that we could capture the geometric fidelity or the beauty that we know to be nature. And so, let's show it to you now. Tony? This is what it's like to be a Top Gun pilot.
This is Medved. We have enemy fighters approaching the transport. Indeed. Choke off your throttles. Break off and go after those fighters. This is Medved. 2 minutes to go. Good hit.
I think Clay is back there flying. Clay, you're going to take us closer to the terrain so that we can see the amazing geometry? So you're looking at a particular level, and as I said earlier, 128 square kilometers, basically the entire Bay Area, where each triangle is only as small as 2 meters.
Proceed to waypoint 1 and engage ground target.
It's a state-of-the-art flight simulator. This is a level of flight simulation technology that I don't think any pilot in the world has ever used. So any gamer today could be a Top Gun pilot. Hey Clay, thanks very much. Appreciate that. Round of applause. Let's put our hands together for the guys at Ubisoft. Amazing game. HOX 2 coming up soon. Almost exactly 4 years ago, we introduced our first GPU with the revolutionary CUDA parallel computing architecture. The observation that we made was that the 3D graphics processor, which was massively parallel to start, could be evolved into something that is more general purpose. And we thought that there would be all kinds of applications where if we were to combine the multi-core CPU with a many-core parallel processor, we could speed up those applications dramatically. And we observed that these applications, although some 5% or a very small percentage of the code, 5% or so, a few percent of the lines of code, can represent the vast majority of the runtime. So imagine an application where 5% of the code can be parallelizable, but that little part of the code represents 99% of the runtime. Now there are many applications like this, as it turns out. And so we created this many-core architecture, and the architectural name was called CUDA. There were 2 things that we did really, really well with CUDA. The technology invention, of course, was very important, but there were 2 strategic decisions that we made that I thought really made a difference in how CUDA was accepted all over the world. The first thing that we did was this, that we recognized that we don't want to replace the CPU, we just want to add to it. To add to the multi-core CPU, the many-core architecture of the GPU. And so as a result of that, there's never any slow down. It's always speed up. The second decision we made was to ride the back of the high volume GPU business we had called GeForce.